There are two main types of phenomena in our world, light and matter. But what are they really? It was to try and answer that question that at the turn of the 20th century, physicists began constructing the quantum theory. Up until then, physicists divided natural phenomena into two categories, waves and particles. A particle, a rock for instance, is an object that is confined in space. Its position is easily determined. However, the wave created when the rock is thrown into the water spreads out in all directions. It is a continuous occurrence that cannot be confined. Early in this century, it was thought that light was made of waves. Indeed, every color in the light spectrum was seen to match a different wavelength. The red waves being, for instance, about twice as long as the blue waves. Conversely, atoms, small bundles of matter, were seen as particles, themselves made up of smaller particles, namely a nucleus around which one or several electrons orbited. However, a simple observation challenged these models. If, for example, a block of iron is heated, according to classical physics, it should emit the entire spectrum of light wavelengths. But that is not at all what is observed. From its initial black color, the block first turns red, then white. Finally, it turns ultraviolet. The block of iron seems to jump from one wavelength to the other. This challenged classical physics. To solve the puzzle, physicists were forced to admit that light is produced in the form of minute particles of energy, photons. Each photon has a distinct color. The successive color changes in the iron block are due to the fact that at a given temperature, the block's atoms emit mostly photons of the same color, corresponding to that temperature. But physicists also realized that the atoms themselves were not as they had imagined. Contrary to what they believed, the electrons do not have a fixed path around the nucleus of atoms. For example, on the surface of the sun, atoms collide violently. These collisions send the atomic electrons on to a higher orbit. They then fall back to their initial orbit, releasing a photon of light. It's a little as if the electron went up a stair and then back down again, each time releasing a specific amount of energy. A same electron can orbit around the nucleus following more than one path. Taking their research a step further, physicists observed that the number of paths an electron can take is in fact infinite. In other words, it is impossible to know the position of an electron at any given moment. One can only assess its probability of existence at a specific location. That probability of existence may be represented by a fuzzy wavelength floating round the nucleus of the atom. Through these findings, light, thought to be a wave, also became a flux of particles, and the electron, thought to be a particle, also seemed to possess wave-like properties. This new concept of light and matter revolutionized scientific thinking. Until then, it was thought that in nature, a same cause would always produce the same effects. For example, by knowing the position of the ball he is aiming at and exerting a given force on his cue, an experienced billiard player would probably sink his ball into the pocket. But if the billiard balls were to display quantum behavior, things would be altogether different. When motionless, the balls would be quite visible. But once in motion, their path would be such a fuzzy cloud that it would be impossible to locate them. Even worse, the balls might go in a direction diametrically opposed to the path intended, going, for instance, 180 degrees off the chosen direction. Even an ace player would have little chance of hitting the mark. Fortunately for billiard players, the quantum theory applies generally to the world of the infinitesimally small, and with great success. For example, thanks to the quantum theory, a microscope has been developed that can see atoms, something once thought impossible. The principle of the tunneling microscope is simple. It is a tiny probe with a single atom at its tip that images surfaces. The tip scans the surface of the object being studied so closely that the electronic cloud of the atomic probe and that of the object's atoms overlap. An electric current then goes through the space in between. The smaller the distance between the tip of the probe and the object, the greater the current's intensity. By scanning the surface of an object, we can provide an extremely accurate map of that surface. In some cases, the map will reveal what no microscope has ever been able to show: the material's individual atoms. While he himself was one of its founders, Einstein found himself in disagreement with the quantum theory. God, he said, does not play dice. These fascinating images, however, would seem to prove that the game of dice is indisputably one of God's favorites.